Thin film interference. Suppose we have an extremely thin, we're talking like hundreds of nanometers thick, film like a soap bubble. The soap bubble is transparent, has an index of 1.35. The air on either side has an index of 1. So in any of these thin film situations, what we have is light is trying to go through. Now whenever you hit a surface, some of the light will transmit, some of the light will reflect. So let's look at that in detail though. Because we have two surfaces, now we have the possibility for the waves to trip over each other, right, in destructive interference, or add up to a much bigger wave in constructive. So let's see which happens. The four beams, it's always the same four beams that we want to compare, is the beam that goes straight through, the beam that reflects here, the beam that reflects here, and the beam that zigzags and goes through. All the other beams will just be repeats of the same math, so we don't need to bother. If we want to know what's happening with the transmitted light versus the reflected light, there's going to be a condition. There's going to be a condition for constructive interference and destructive interference. And there's going to be the condition for transmitting and for reflecting. And those two will be swapped, because if the light goes through, it's not reflecting. If the light's reflecting, it's not going through. That's why on either side of these, the formulas will be swapped. It will either be, if this is a width W, 2 times the width could be m times the wavelength, and don't forget to shrink the wavelength for the index we're in. It's always the index in the middle, because that's where the extra path is. One of them is going to be 2w m lambda over n, and the other is going to be 2w m plus a half lambda over n. And we want to know which is which. And for that, we need to pay attention to phase flips. If light bounces off of a harder, more optically dense material, it will undergo an inversion, a phase flip, a shift of 180 degrees. However you want to say it, it's as if it got a free half a wavelength. Which means if you tried to do it immediately with itself, it would interfere destructively. So let's see what happens in all these bounces. This bounce, one bouncing off of 1.35. If you bounce off of higher, you flip. That's a flip. This is 1.35 bouncing off of 1. That's lower. We don't flip. Again, 1.35 bouncing off of 1, and 1.35 bouncing off of 1. So in this whole picture, the only phase flip is right there. So let's look at the transmitted light, because that's simpler. It has no phase flips. For the transmitted light, with no swapping around from phase flips, the constructive transmission that condition will be that 2w equals m lambda over n. And the destructive is that 2w is m plus a half lambda over n. The light that reflects has the two conditions swapped. So reflected light is constructive when 2w equals m plus a half lambda over n, and destructive 2w is m lambda over n. So working that out was the point of examining the phase flips. So transmission means the light goes through. If the light fails to reflect, it transmits. If it fails to transmit, it reflects. So they're opposites. That's why these are always swapped, and the point of the flip was to figure out which one was which. If these indices were in a different sequence, like 1 to 1.35 to 1.5, there might be a different arrangement.